And last one, double tapped. Both sides I'm going to have L1, L2, C1, C2. Combination of the tapped capacitor and tapped inductor. You can see at the input side I have L1, L2, and I'm giving input across L2. At output side I have C1, C2, and I'm taking output across C2. In certain case, some component values may be impractical or it will be difficult to match. In that case, we are forced to use these type of matching networks where the capacitance or inductance may appear to be excess. So to reduce that, I split the capacitor into two and I take output across one capacitor. So I have so many degrees of freedom here because I use four elements, right? So I have the option to choose my Rin either across L2 or L1, and I have the option to choose R2 across either C1 or C2. So the more flexibility I have in this circuit. So this circuit boosts R2 to a larger effective parallel resistance across the entire tank network and then reduces the resistance into Rin. So what they say is they effectively, when you consider the image resistance at this point, R2 will be reduced. R2 will be increased to a point at the image resistance, and from here Rin will be reduced. Okay, so it is going to perform increasing value of R2 to the image, and from the image, the value of Rin is going to be reduced. So that is how this double tap resonator is going to work. And this technique, therefore, increases the required inductance, simultaneously reduces the required capacitance. So definitely, if you are applying input resistance across L2, I will ensure that my inductance value is larger. And if I want to reduce the impedance, I'll ensure that C2 value is smaller. So Rin will be matched to R2. So I have the flexibility. That's what they say here. You have the flexibility to choose across what element I'm going to give my input resistance and across what element I'm going to take out my output resistance. So this double tapped matching network has four components. So it has 4 degrees of freedom. The degrees of freedom now, or how much flexibility you have in choosing the component value. So that is going to be degrees of freedom. So tapped resonator is going to have 4 flexibilities for me. So I can choose wherever I want to give Rin and I can choose wherever I want to take R2. So it is going to have 4 degrees of freedom. So we may specify 4 parameters here: center frequency, impedance transformation ratio, quality factor, one more thing, capacitance or inductance. Across what component I'm going to measure the Rin and RL values. Although everything seems to be good in on paper, we have derived so many types of impedance matching networks on paper, but nothing is efficient unless you have inductors and capacitors which are physically realizable at that particular frequency. Unless you are able to have a very good quality factor, physically realizable inductors, then all these circuits will be very good on paper and it will not work. It will not work better when you use it for the real-time applications. So these are different types of impedance matching networks, whatever we have seen. So we have seen what is impedance matching network. We have seen L-type matching networks. We have seen uh, T-type. We have seen Pi-type, and we have seen double tapped capacitance, double tapped inductor, and combination of both. Okay, so tapped inductor, tapped capacitor, and double tapped resonator we have seen. So these are going to be the different types of impedance match